really stop to think about how computers actually think? We're about to go under the hood and peel back the layers. You see, they don't think in words or numbers like we do. They speak a language of pure logic. Let's dive right in. So let's kick things off with a little mystery. When you type the number 25 into your computer, what does it actually see? I can tell you it's not a 2 and a 5. No, it sees something completely different because it's speaking a language that's way more fundamental than our own. And that native language, well, it's called binary. It is a system built on just two symbols, 1 and 0. That is it. Every single thing a computer does, from running the most complex software to just showing you this screen right now, is all built on that simple but incredibly powerful foundation. So if we really want to get a handle on how to work with data at its very core, we first have to become translators. We've got to learn how to convert our familiar decimal numbers into binary, and just as important, how to change them back again. You know, the easiest way to do this is with a method called divide by 2. It's exactly what it sounds like. You just keep dividing your number by 2 and jotting down the remainders. Let's give it a shot with our mystery number 25. And voila! After running through those steps, this is what you get. 1, 1, 0, 0, 1. That sequence of ones and zeros, that's how a computer actually perceives the number 25. Okay, so what about going the other way? Well, it's just as straightforward. Each position in a binary number represents a power of 2, starting from the right. All you do is multiply each bit, the 1 or the 0, by its position's value, and then just add everything up. So now that we can speak the language, it's time to learn how to give commands. You see, C programming gives us this really powerful toolkit of what are called Bitwise operators. They let us manipulate these ones and zeros directly, which gives us an incredible amount of control. First up, we've got the Bitwise AND operator. I want you to think of this one like a super strict bouncer at a club. To get a 1, both bits in the exact same position have to be a 1. If even one of them is a 0, nope, the result for that spot is 0. Okay, let's see how this actually works. We're going to compare the number 5, which is 0, 1, 0, 1 in binary, with the number 3, which is 0, 0, 1, 1. If you look column by column, starting from the right, only the very last position has a 1 in both numbers. And that's exactly why the result is 0, 0, 0, 1, which is, you guessed it, the decimal number 1. All right, let's move on to the next tool in our kit, the Bitwise OR operator. Now this one is way more relaxed than AND. To get a 1 in your result, you only need a 1 in either of the original numbers for that position. So if we use our same numbers, 5 and 3, we get a totally different result this time. The answer is 0, 1, 1, 1. So why? Well, if you look at the columns, you'll see that 3 of the 4 positions have at least 1, 1. And that binary number, 0, 1, 1, 1, translates right back to the decimal number 7. Now for a really interesting one, the exclusive or as it's usually called XR. This operator is all about finding differences. It spits out a 1 only when the 2 bits in a position are different. You know, one is a 1 and the other is a 0. If they're the same, the result is always 0. Let's go back to our trusty 5 and 3 one more time. Check out the 2 middle columns. In one, we have a 1 and a 0. They're different, so boom, we get a 1. In the next one, we've got a 0 and a 1. Different again, so another 1. The final result is 0, 1, 1, 0, which is the number 6. Okay, the complement operator, sometimes people call it the NOT operator, is probably the simplest one of all. It's basically a light switch. It just looks at every single bit in a number and flips it. Every 0 becomes a 1, and every 1 becomes a 0. Simple as that. So if we take the number 5, and we're showing it here as a full byte with those leading zeros, and we apply the complement, every single bit gets inverted. Now, here is where things get a little wild. Computers use a system called 2's complement to represent negative numbers. And in that system, this new pattern, 111, 111, 010, actually represents the number -6. It's a bit of a mind bender, I know, but it's a super efficient way for the computer to deal with both positive and negative numbers. All right, our last set of tools are the shift operators. And these are incredibly useful because they let us take a whole pattern of bits and just physically slide it over, either to the left or to the right. A left shift does, well, exactly what it sounds like. It pushes every bit one spot to the left, and a 0 gets added on the right end to fill in the empty space. But this has a really cool side effect. Shifting left by 1 bit is an incredibly fast way to multiply a number by 2. So here, our 5 instantly becomes 10. And I bet you can guess what a right shift does.
Yep, it pushes every bit one position to the right, basically dropping the last bit off the end. This is the same as doing integer division by 2. So, if we take that result of 10 and shift it right by 1, we get right back to 5. So, we've learned this new language. We've got a whole new set of grammatical rules. But you might be wondering, why does any of this actually matter? Why would a programmer ever need to get their hands this dirty at such a fundamental level?
Well, this entire toolkit that we've just gone over, and, or, XOR, complement, and the shift operators, it is not just some theoretical puzzle. It gives a programmer direct, fine-grained control over the raw data that's living inside the machine's memory. And that kind of control is absolutely crucial for anything where performance is key. We're talking about high-speed graphics, writing the code that talks directly to hardware, creating compression and encryption algorithms, all the way down to just efficiently turning features on and off in a program using single bits as little flags. So what's the big takeaway here? Understanding and using these bitwise operators, it unlocks a whole new level of programming power and efficiency that you just can't get any other way. It's all about speaking the computer's native language to make it do exactly what you want as fast as humanly or computerly possible. By learning to think in binary and manipulate bits, you're not just writing code anymore. You're engineering at the most fundamental level there is. You're one step closer to telling the machine precisely what you want it to do in the language it understands best. So the only question left is, what are you going to tell it to build?